So now you hopefully see my slides, and this is on a different workspace here, so I don't see any chat or something like that. So all questions go to the end. Yeah, and then I probably can switch on my camera as well, so that at least you can hear me. Okay, fine. And so, well, I only got about a couple of hours sleep last night, so I hope this presentation still goes well. This actually continues something that I talked about 3 years ago in Bochum at emBO 2019, where I already proposed to use standard C++ as API. And but at that time, I proposed more or less to base it on something like free RTOS or something like that. And then after looking at it, I found that it's not quite matching. So I eventually decided, okay, I will simply write my own operating system based on C++. And so this is C++ OS. And I will show quite a lot of code, and if you want to have your own look at the code, you can find it here at GitLab, and I will also have this reference again at the end of my slides. And so I first talk a little bit again about why we actually want to do that. It's more or less what I already talked about 3 years ago. And then I really will talk about C++ OS because that's my baby. And of course, I'm very interested to talk about it. So yeah, C++ OS is just one specific implementation, but the whole point is, well, operating systems normally provide an interface, an API, so you can use the facilities of the operating system. But I believe that C++ now has enough interface so that you don't need any OS-specific implementation or any OS-specific API. So C++ OS is one implementation, but actually the API is just a standard API. And so I hope in the future we will have more operating systems that simply just provide that interface. And however, C++ itself cannot provide everything because a C++ compiler is not an operating system. So there is no runtime part of the C++ compiler. And at the end, I will also talk a little bit about the implementation of C++ OS. And yeah, let's see how much time we will have for that. And yeah, why do we want to do that? Well, there are a couple of reasons. And the main reason, of course, is portability. So yeah, with operating systems, with small operating systems, you never know when a vendor gets bought by another vendor, and so there is no support anymore for the old operating systems and things like that. So sometimes you simply have, or you have to change to a new hardware and the operating system is not available for that or whatever. So yeah, it would be nice if it's not too hard to switch from one operating system to another. So if you have a standard interface, that should make things easier. And this is only about porting the application to a different operating system. Of course, if you use a different hardware, well, you always have some parts that are hardware specific. Fran talked about using your own abstraction layer for that, and I really recommend that. But still, switching hardware is generally quite a big task. And but even if you only port to a new operating system, and even if the API is the same, so it's a standard C++ API, so it's the same, porting is still something you have to do because not everything is covered by the standard library. So for example, the configuration of your application, how big your stack is and things like that, the setup of your system, that is not covered by the standard C++ API. So that will be specific to a concrete operating system. And of course, you have to do all the testing again. Well, about your existing operating system, you probably know about quite a number of bugs. If you switch to a new one, you have still to learn, okay, what bugs does that one have? And if you have to do certification for safety reasons or something like that, you have to do all of that again. But it's much easier than to port to a different operating system with a completely different API. And typically, you can reuse nearly all of your application code and as well nearly all of your test cases. And that is definitely helpful. And of course, if you use the standard C++ API, well, you have that on your host as well. So you can run quite a lot of your target software on the host and do a lot of tests on your host. Of course, it's not the same as running on the target, and you have to do testing on the target as well. But some things are simply impossible to do on the targets. So for most targets, for example, you don't have the nice things like address sanitizers or thread sanitizers or things like that. And well, in a project I worked on, we had test scenarios where the equipment for that scenario cost nearly $1 million. So you simply cannot do that all the time. So you cannot integrate that in a CI system. So if you can do it on your build server, you can test much more. And also, debugging is often much simpler on the host than on the target. And of course, if you want to run things on the host, you need to do some kind of mocking for your devices, for internal functionality of your MCU, like timers, watchdog, and things like that. And for that, it definitely makes sense, like Fran said, to provide your own abstraction layer. And then if you do some simulation or mocking, well, you have to think about how far you want to go, and timing is one of the things there. So a number of processes take quite some time on the real hardware, and sometimes you are tempted to shorten that by running just faster on your host. But sometimes that timing is really important, and then you need to make sure that the timing for your tests on the hosts are more or less the same than on the target. And the other thing is for all the error paths you have, For mocking, it's much easier to introduce or to inject errors, like drop packets from a serial line or simply flip flash bits or things like that. And most of these things should be reusable if most of your application simply uses the standard C++ API. And then also, well, you can expect that new developers know about standard C++. They will probably not know about some specific operating system that only a few hundred people in the world use. And so that makes it a lot easier to maintain the code base over a long time. And the other thing is that if you program against standard C++, you can actually reuse a number of components from other projects. And this is the next topic. So you might actually build control structures and use them as building blocks. And here's my favorite example. So the example is you have a data concentrator, and the concentrator actually has two producers. So you have two lines where data comes in. And for each of them, you have a filter that just throws away data where the checksum doesn't fit or things like that. And then you actually put them together, and then you have a common filter. And and then for that, you only have one consumer, and that finally stores it somewhere. And the point is, well, one of your data comes from a line that has really critical timing, so that producer should have a higher priority. And of course, sometimes you do some other things on your system. So at least the normal priority tasks might get delayed a little bit. And to not lose any data, you want to have some buffers. And so this is what you can set up using sender receiver. And Paul talked already yesterday about that. So, and he talked about having a sender that is an interrupt service routine. And I've more or less exactly the same. And same as Paul, this is only slide code. I don't have this specific thing working yet. But yeah, I hope I get it working, hopefully sometime soon. And well, when I feed the output of this interrupt service routine through a buffer into application code task. But this is one that has higher priority, so this gets higher priority. And this is the size of my buffer. And then I have a function that simply filters the value. And this one here actually will be a standard algorithm. And it will, and all this together will give you a sender back. And so this is a setup. And then you do it for your second data source. Here you just have a normal priority task, but you also have a buffer. And you get another sender back, and then you want to put them together. So you use a when any, and you give it your two senders. So these are the input to the when any. And after that, the output of that one, well, whatever comes in will be sent to the validate function, and the output of the validate function will be sent to the store function. So this is how sender receiver looks like. And the whole sender receiver interface is essentially an event interface. So senders provide more or less events, and receivers handle those events. So instead of registering a callback for a specific event with sender receiver, it looks like this. So you more or less pipe the output of the event into a callback. And some details are still open. So one of the big open issues for me is what roles buffers and queues actually play. And this is actually something that the people who developed sender receiver already promised 4 years ago to write a proposal. I still haven't seen that proposal. But well, we now have a little bit more time because it was planned for C++23, but it was decided, okay, no, we will only have it for probably C++26. And Neil Douglas is working on a proposal that provides networking on top of sender receiver. So now let's look at actually how C++ OS looks like. And this is actually working code. So this is not slide code. And well, working code, it works here. If you look at the code at GitLab, you will note that there are no make files, but because the make files are pretty ugly and are very specific to my environment here, and I have to come up with a better build system. And so this is currently missing. And also you really need, well, it was only tested with a GCC 12 tool chain. So anything, and then GCC 12 is not yet released. So I actually built my own tool chain based on the current Git master. But then, well, here's an example. So I actually have a scheduler. Well, the point is this state execution also comes from the sender receiver proposal. And the names there are not exactly what embedded persons typically use. So normally, at least for me, a scheduler is something that makes scheduling decisions. And this is not the case in the sender receiver proposal. Actually, what does the scheduling decision is the so-called execution context. And this is something that my operating system provides. And then this execution context can give you schedulers, what sender receiver calls schedulers, but these schedulers are only very lightweight handles on top of the execution context. And so my execution context actually provides a scheduler as a template, and as template parameters, you give first simply an ID for your task. And the next one is the stack size for the task. And then you can also give a priority. Here I don't give a priority, so everything runs on the same priority. And if you don't give a stack size, then you will get a default stack size. This here will be standard. This one, of course, has to be provided, and this one has to be provided by the operating system. And yeah, I have a number of tasks. So the first task is a very simple task that simply switches an LED on and off. The next one is a print task that every 10 seconds prints out some information. And then I have a number of busy tasks. So these one, most of the time, just sleep. These ones actually run all of the time. So they simply increment the counter, but the point is for this you really need a real scheduler, because if you have tasks that take up all your CPU time, you need somebody to say, okay, who is allowed to run when. Well, and this only registers those tasks with the execution context. And here we actually started. And this should never return. So here are the tasks. So here's the LED task. So I have flash rate of 800 milliseconds, and this is the specific GPIO I use for my LED. So this is a private class that simply wraps a GPIO, and so my LED task simply does forever a standard sleep 4. And then it just toggles the LED, and then we go back to our sleep. Then the busy task, well, that, as I said, it simply increments a counter, and then that is a local counter here. And whenever it gets to 1 million, we reset the counter and increment a global counter. So we have a global counter, one for each of the busy tasks, and so that gets incremented. Here I use volatile, which is not completely correct. I will come back to that later, but because the problem here is I'm running on an AVR. So this is 8-bit. So writing or reading 4-byte value, well, that might tear. That might be interrupted. So this should definitely be an atomic, but I will come to atomics a little bit later. And I even have to make the local count volatile, because if I don't make it volatile, if you look at this code here, the compiler doesn't see anything external that might access the count. And you don't have any synchronization or anything like that. So it turns out that the old compiler, GCC5, that actually compiled that fine. But at least starting with GCC8, the compiler simply optimized all of this away. So I really need the volatile here. And then finally, my print task. So I have a class and an object debug out that has a write function. So the write is more or less standard, but I haven't figured out how to customize that. So the class here is not really standard. And you just give it a pointer to void and the number of bytes you want to send. And so I have a buffer here, and I have a print period of 10 seconds. So I always sleep for the 10 seconds. And then for all the 3 counters that I have, I use the toCars function from C++17, I believe, and just print my counter to the buffer, and then I get back the pointer to the next byte. So here I add blank, and here I actually also give the internal count. For that I have the count pointer, and then I add a line end, and finally I write it out. And these are all the headers that I use in this application. And all these are just standard headers. And the point is GCC 12, the current master, actually built the libstdc++ for you on top of AVR libc, and that provides nearly everything. So if you don't restrict it to freestanding, you get nearly everything. Well, of course, only nearly. And so, for example, the thread header that doesn't provide a lot. And I right now don't provide a lot here as well, but I have to provide the sleep for. So I provided that one. And in the chrono, I had to provide the now. But this one and this one, I just could take from libstdc++. This one, of course, isn't standardized yet, so GCC doesn't have an implementation there yet. So I had to provide it, but it only contains what is proposed for the standard. Well, yeah, and then this is the header for my operating system, and these are my private helpers, and this is specific to the hardware. So this is more or less the abstraction layer, and this is hardware. But yeah, more than 90% of my code simply only use this part. So yeah, Paul already talked about freestanding, but the point is that there's a lot of stuff that even with Ben Craig's proposal will not be in freestanding, but is still useful. So GCC libstdc++ actually tries to provide everything that's possible if you have an underlying C library. So for ARM, it uses newlib. For AVR, it uses AVR libc. For MSP 430, I don't know exactly what it uses, but I know that that is the test platform for Jonathan Wakely. So my operating system simply has to fill in the gaps. And yeah, here for chrono, everything is there except now. For mutex, so things like lock guard and unique lock, they are there. Just mutex itself is missing. So I only have to provide the mutex. And with that, I come to the things I actually provided on top of that. And the first one is atomic. So Odin talked this morning about his tool chain doesn't provide atomics for small arm. GCC 12 actually provides them for a small arm, but based on the old implementation by Lawrence Kraull and Hans Böhm, the more or less reference implementation, more or less based on loop with atomic flag and test and set. And that is not really what I would use. So typically what you use on something like AVR is you just do disable interrupt, do your operation, enable interrupt. And this is essentially what I provided. So I provided the atomic header using disable enable interface interrupt. And with that, well, I made this atomic, and the reason why I had to make this atomic as well is because I actually publish a pointer to that, so that you don't get any tearing. This really should be an atomic. And of course, my global counters should be an atomic as well. And even these are manipulated, well, written from one side, read from the other side. So this should be atomics as well. And 8-bit, of course, is special because there the load and store is always atomic. So you don't need the disable enable interrupt. So I have a special implementation for that one, just a specialization, a template specialization. And so one of my busy tasks now uses an 8-bit counter, so I could look at the assembler to check that the correct code is produced. And the interesting thing is because it's an atomic, the compiler knows that it shouldn't optimize it away. So here I don't need the volatile. And then the mutex. So I actually implemented that as well. And so I decided to start my 3 busy tasks delayed. So I have a mutex to control the startup, but because I cannot initialize the mutex locked, I also used a start flag. So in my main program, I initialized that start flag to false. And I have an additional control task now. And now my busy task, well, it first waits, that does a busy wait for the start flag to make sure that it really waits for the mutex to be ready. So actually in all of my test cases, this was always already set to bool, because my control task has a higher priority, but you're never really sure. So I decided to have that start flag anyway. And so this is just a busy wait, but now this one is the real mutex lock, because here I have to wait for the mutex to be available. And so the control task actually first locks all the mutexes, and then it can set the start flag to true. And then it always simply waits, sleeps for 2 seconds, and unlocks the next mutex. And that's it. And then, of course, we also have condition variables, and that is actually the better way to wait. And well, maybe one thing, so I have implemented mutex, I haven't implemented semaphores yet. But semaphores actually would have made it easier, because for semaphores, it is allowed that I lock the semaphore in the main task and then unlock it in the control task. For mutex, that is not allowed. So there is a reason why for the mutex, I can only lock it in the control task, and then that is why I need that start flag. But then to condition variable, and so now my start flag is just a normal bool, and it's initialized to false. And I have, for each task, I have a condition variable and a mutex. So my busy task now simply can wait for the condition variable. So I have to lock my mutex, and then I simply wait on my condition variable and give the wait the unit lock. And I have to do that in a loop, so that I check the flag again, because I could have spurious wake-ups. And so the control task now simply locks the mutex, sets the flag to true, then it unlocks the mutex, and then it does the notify one. And we had yesterday the talk about synchronization primitives, and that said that this is not always safe. I think that is not true, because you always have to do this loop here anyway, either internally of wait, but by just giving a predicate, or by doing the loop itself because of spurious wake-ups. And if you have that loop, then it doesn't really is a problem that if after the unlock and before the notify one, somebody modifies that start flag again. And the point is, if you don't do the unlock before the notify one, well, the notify one actually the scheduler actually looks who gets notified, and if that who gets notified has higher priority, then it immediately switches the context to the high priority task. And now if you still have the mutex locked, then that has to block again on the mutex, and you have to do a context switch again. And so I think it's actually better to do the unlock before the notify one. Yeah, and that's essentially it. Now, with mutex and condition variable, I can use or I can implement a standard queue. And queues are actually pretty important. If you heard Odin's talk this morning, well, he had the ring buffer, but that is essentially a queue. And so we actually have a standard proposal for queues. And yeah, the point is you need, if you want to do it in an interrupt service routine, you need non-blocking push. And there are several options for that. And I simply took the easy path. So the standard the proposed queue, and that will probably go to concurrency TS2. It will. There's currently no standard vehicle for that, but it will go to a TS, and I think that's good because it will probably change before it gets standardized. But that is fixed size. There might be lock-free versions. It essentially has a push, pop, and close interface, and it also has single wrappers, and it has a iterator interface for debugging only, because that iterator interface is, of course, not thread safe. So this is more or less the proposed interface. You have a status. For my implementation, I actually added one status, which is would block, and I will come to that in a moment. And then there's a close interface, and then there is the, I will not talk about the value, but here are the push. Well, no, this interface is not so interesting. I like this one more. So here is the wait pop and the try pop interface, and the wait push and the try push interface. So this one blocks, this one doesn't block. And so I actually already had my implementation, and that is a host implementation, and I didn't change anything for the embedded version. And so here is the implementation, and here we have the wait pop. And so this is just the standard implementation. You grab the lock, then you wait on not empty, and then you check, and also you have to you check for the emptiness and for the not closedness. And then you have to check whether you got an element. If so, you just return with that element. And otherwise, you return that it was closed. And again, then you do the unlock and the notify. The more interesting one is the try pop, because again, you grab the lock, but because you are not allowed to block, you have to give the unique lock, the constructor, the try to lock. And if that was not possible, then I simply return would block. So I return immediately. I always return immediately. I never block. Then I check whether it was closed. To be honest, this is probably a bug. Because this way I might lose the last value, because even if it is already closed, there might actually be still values in the queue. So this is buggy, and then the point is the try pop. This is something I only added here for this presentation. So I didn't look too closely to it. So this is a bug to do it here. Sorry. And but I'm never allowed to wait on something here. So I check here. Yeah, I simply should turn around those two if clauses. So if it's 0, I just return empty, and otherwise I have a value, and then I can just provide the value and return success. And now, based on that, I have actually other tasks. So I have restructured my thing a little bit. So I only have the print task, and then I have 4 tasks, 2 for the try and 2 for the blocking queue. So I have here my try queue with a size of 10 and the blocking queue with a size of 5. And I put in 16-bit ints in there. And I actually have another queue for the printing, so that printing is easier. And the try fill, well, that simply does a try push. And the try get does a try pop. Even if I'm not in an interrupt service routine, I still can use the try interface. And the block fill, that will use the wait push. And the block get will do the wait pop. And of course, these are blocking. And yeah, I'm now running out of time, so I will only go very quickly. So the sender receiver, well, it's not clear what queues actually play a role, but the whole point about the sender receiver thing is that you can customize things. So you can provide a customized queue, for example, between an interrupt service routine and your application task. Well, and for the implementation, yeah, you have to port it to your hardware, and it's not really a lot of stuff that you need to do. So you have to provide a function that that creates an initial stack. But the main thing is this one. So you have to decide on an interrupt, and you have to have an interrupt handler that does a task switching. And so, you have also to implement the context switch. And yield also provides a context switch. And then I need to be able to interrupt, to disable interrupts and enable that again. So you need to provide that as well. And for the time, you need to provide the now. And I actually started for a port to an ARM Cortex-M4 without FPU. Actually, my hardware has an FPU, but I couldn't figure out how to decide whether I have to save the FPU state or not. So I decided, okay, for now, I don't have that FPU support. And after the initial example worked with that, I switched over to the AVR, AVR6. So your program count is actually 3 bytes. And that turned out to be much harder because the ABI for the compiler for AVR is just horrible. And so it took much longer. And then I worked on that one. And most of the things I actually tested on SimulAVR. And so that is where I tested all the other things. So right now, the ARM port is not really tested. And yeah, you have to say somewhere, okay, how many tasks you have and things like that. And yeah, the implementation itself is really very small. So yeah, this is more or less, it's 220 lines. Well, it's not all of it, but it's really most of it. And so it's actually pretty simple. So there's not a lot here. And for the library, well, the point is I just have a scheduler which looks for priority, and otherwise it just takes the next task more or less. It provides an event class for everything that needs to block with some functionality there. And whenever I have to provide something in a standard library header, I simply provide that header, and then I do the include next to get the header from libstd C++. And I use disable interrupts quite a lot, and the scheduler is not preemptive, and it's single core only. And why should you use it? Well, you don't. You shouldn't use it because it's definitely not production use. It's actually really a playground for me to try out new stuff. So the point here is I really wanted to implement the sender receiver stuff. And so I decided, okay, I will provide my own scheduler. So it's much easier to implement that. And yeah, it has a lot of overhead. Probably you don't want a scheduler on very small systems. And so coroutines can actually be much better. And I don't really have time now to talk how you can have interrupt service routines with coroutines, but we can talk about that right after the talk. And yeah, GCC actually provides the standard C++ library, and it's really useful. So here I actually have a test code that uses string and vector without mallocs. So I actually use memory resource, and I have my own static allocator that just uses a monotonic allocator. And yeah, that's it. Here you have the reference to my code again. These slides are not up yet, but they will be up at my website. And the executor proposal, you can find it here. It's P2300. And oops, so sorry, I didn't want to provide this one. I wanted to provide the one for the queues. Sorry, I messed it up. But it's also in 2018, and you will probably find it. Otherwise, send me an email. And that's it. I probably already overstepped my time. So we probably have to answer the questions on the side. So I will now leave the podium.